Okay, we're looking at this problem of a horizontally launched projectile. A ball could be pushed back here and it gets to the edge of the table and becomes a projectile. It goes into free fall, where gravity is the only significant force acting, which means a sub x equals 0 and a sub y is 9.8 meters per second squared downward. We defined a coordinate system where right here at the moment it's leaving the table is the origin. So if up is the plus y, to the right is the plus x. We could have made the origin down here, and then that would have changed our y value. It would have changed our y naught value. Wouldn't have been 0, but x naught still would have been 0. It also would have changed our y value down here. So again, we picked the origin here. We could have picked the origin to be there. In this problem, our initial velocity vector diagram looks like this. Okay? Normally our initial velocity vector diagram is a triangle, but in this problem it's not a triangle because it's a horizontal launch. And when it's a horizontal launch, then v naught y equals 0. And if v naught y equals 0, then we know that the launch speed is equal to v naught x. And we also know that vx is equal to v naught x. So we're supposed to find out the launch speed, okay, how fast. So it really just wants speed. We're not finding velocity in this case, just the magnitude. And so any of these would do. We can find this, or this, or this. The range is 3 meters. So if we look at this distance, okay, drop straight down to here on the floor, and it's 3 meters over. Okay, and it goes down 1 meter, which is why this is a negative 1 meter for our y value. All right. I like to split these up into the horizontal equations that I put over here and the vertical equations over here. Remember, in the horizontal direction, the only equation from your equation sheet that's going to be useful for projectile motion is this one. And we know ax is 0, so it simplifies down to this. Any of those other equations from your equation sheet aren't going to add anything to our understanding of any of these projectile motion problems. Okay? And we know x naught, but we don't know the time, and we don't know what v sub x is. However, if we can find the time, then we can use this equation to find v naught x, which we know is equal to vx, which is equal to v naught, which is what we really want. And I should put that here. That's what we're looking for, is v naught. I accidentally had that as v. It's definitely v naught that we want to look for. All right, so what about the vertical direction? Well, in the vertical direction, we have our position equation, y equals y naught plus v naught yt plus 1/2 ayt squared. And if you didn't think to use this equation first, that's okay. You go through the process, you pick an equation, you see if it's going to be useful or not by adding the checks and question marks. So we do know y and y naught. We know v naught y, that's 0, so that's going to make that go away entirely. And we know ay. So therefore, we're going to be able to use this to find the time, and then we can plug it in here to get v naught x, which is then equal to v naught. So let's go ahead and do that. So I'm just going to make a note. We're going to do this first, and we're going to do that second. So I'm taking this equation down here, and we'll fill in our values. Negative 1 meter equals 0 plus 0 plus 1/2 times negative 9.8 meters per second squared times t squared. And then we solve this and we get t equals 0.45 seconds. And just for an extra significant figure here, it's actually 0.452 seconds. Now we can use that in this equation. So we'll bring this one down, and we'll say that our x value, we know that's 3 meters, x naught is 0, plus v naught x times 0.452 seconds. Okay, so this went right into there. And now we can solve, and we get v naught x equals 3 divided by 0.452. We get 6.64 meters per second. And v naught equals v naught x, so v naught equals 6.64 meters per second. Okay, our velocity here came out to be a positive value to the right, and so the sign makes sense. It's obviously traveling to the right when it comes off the table. Did we solve for everything we needed to? It said how fast, so we got that. As for the speed, the magnitude of the velocity. Correct units? Yes, we had meters here. We divided both sides by seconds, and we got meters per second. Over here, it didn't talk about the units, but we had meters, and then we divided by meters per second squared, and then we took the square root. So I can simplify this by saying seconds squared per meter over seconds squared per meter. So all of this is just 1. Okay, I'm showing what happened here when I had meters divided by meters per second squared. These units cancel, and meters cancel, and that leaves us with seconds squared, but remember we're also taking the square root, and so that gives us units of seconds for our time right there. And then is the magnitude of the answer reasonable? That's about 13 miles per hour, and that's, who knows? It was projected off the table. It's not 1,000 miles per hour, so that's good. It's a reasonable value as far as we know. We don't know how it was projected.